So today we'll do non-dimensionalization. The recording is on, yeah. Now, this is a very important concept in numerical computing. It will become clear as we go along. So, basically, error is significant for small numbers and large numbers, right? We doing error analysis. I showed you that error becomes quite significant if the numbers are too small or too large. So it's not a good idea to use parameters which are too small, like Planck constant. We should not put as is, okay, or atomic size, or nuclear size, or size of the galaxy. It's not advised that you put in the large numbers or small numbers. You should non-dimensionalize it according using the scale of the system. Okay. Now, some of you may not have seen these kind of concepts, but so I will try to go a bit slow. So every system has some scales. Scale is like a ruler is a scale, no? So what I meant is, for atomic systems, what is the scale of the length scale for this problem? A length scale is hydrogen atom can be chosen as a length scale. Size of a hydrogen atom, which is 0.53 angstrom. Okay, so any system we work with, there is certain unit, basically we can construct the length scale using the parameters of the system. Now, if you are working with bacteria, then you can take one bacteria as a scale, like amoeba. Compared to amoeba, how much are other bacteria? Compared to hydrogen atom, what is the size of other atoms? Now, universe, you can take a galaxy and say, well, this is the size I'm going to make as a standard. So we make 1 centimeter or 1 meter as our unit, no, in daily lives, because in fact, for all the measurements which were done that time, okay, human body is roughly a meter size. So 1 meter became a unit or scale. Actually, I will not say unit, is a scale. Okay, so we use appropriate scale so that we work with the numbers like 1, 2, 3, 4, like that. We don't want to work with my height is 10 angstrom. That is not it's not convenient, right? I mean, 1.7 meters. That is more convenient. Okay, 1000.7 is not convenient. Okay, so you use appropriate units. Is that clear? Or appropriate scale, sorry, length scale. Also, the time scales. So time scale for us, it is like hour is a time scale. For atomic systems, hour is not a time scale. It's too large. So for them, nanoseconds or microseconds or picoseconds, these are the time scales. Depends. Atomic transition happens in picoseconds. Okay, so you choose appropriate time scales. We'll not dig deep into this stuff, but we'll use some. I mean, we are going to work with some systems for which I'm going to show you how to rewrite that equation so that we can put in a computer in a convenient way. Okay, so proper units. So you say Fermi for nuclei, angstrom for atoms, light years for galaxies, or you can go even further. You can, for length for atoms, I may choose hydrogen atom. Okay, for galaxies, you can choose one particular galaxy, and size of that galaxy can be chosen as a length scale for your astrophysics work. It's very convenient. You'll see in the next example, we'll see how it goes. So, non-dimensionalized using system scales. System time scale, system length scale, we'll use that, and non-dimensionalized. So in the new equation, we will not be small length scales or large length scales. All will be order 1. So I'm going to start with an example, oscillator. Okay, so the classical oscillator. So the spring mass is m. Okay, and spring constant is k. position of the mass is kx, and is forced with frequency omega f. Okay, so how many parameters do I have in the system? Can somebody tell me how many parameters? You know what is parameter, no? So there are variables which are x and t, but there are parameters, okay, which are define the equation. So how many parameters are in this equation?
4, 3.
4. So m is a 1 mass, k is a second, f naught is 3, and omega f is 4. So f naught is also a parameter, force amplitude. Now, if I do an experiment or computer simulation, if I want to understand the full system, I need to vary all 4 of them. Keeping k, f naught, and omega fixed. What happens if I change m? Okay. Now, if increase m or decrease m, how does the system behave? Or keep m, f naught, and omega fixed, change k. Okay, that's how we'll study. No, I mean, there's a problem given to you, and let's see, इसको बढ़ाते हैं, इसको आगे करते हैं. So we study the system by increasing, decreasing, and see how the system behaves. Okay? But 4 is too many to vary. So we want to decrease the number of parameters. Okay, that's one objective for experiments or simulations. Simulations, this is a very simple system, in fact, which is the exact solution. But for large problems like weather simulation, if you have too many parameters, then it is more expensive. So it decrease the number of parameters by some clever tricks. So one thing is to divide this equation by m. Divide by m. So if you divide by m, then how many parameters? So I can call f naught by m. I mean m will so k equal to m omega naught square. Okay, I define like this. So now, so m will come out of the left side, and I can divide by m to the right. I can send m to the right. So f naught by m is one single parameter. So you don't vary f naught and m individually separately, but you say f naught by m is my normalized force, and is in fact is acceleration. F naught by m is acceleration. So I will say acceleration of the applied force. Okay, so that is a parameter. So I reduce from 4 to 3. Now I would like to decrease it even further. Please note that omega naught, omega f can be very large values for atomic systems. These are omega naught is something like 10 or 15 hertz. For the electromagnetic waves are coming and exciting the electrons of the atoms. So these are pretty large numbers. I don't want to work with large numbers. So what should I do? One trick is this t time. I can make it non-dimensional. So right now time is in seconds. So I want to make time not in seconds, but time is non-dimensional. So in this system, how many time scales do I have? You understand? Now this is a good question to ask. Some of you may know already. So this system has in fact 2 time scales. Can you tell me what are the time scales? Anyone? So you said no, I mean, for hydrogen atom, for atomic systems, hydrogen atom can be the size. In this system, there is a time scale. There are 2 frequencies, right? Omega naught and omega f. They will give you this time scale. So 1 by omega naught is one time scale, 1 by omega f is another time scale. So I'll choose one of them. Okay, and it's more convenient to use 1 by omega naught as a time scale. So I'm going to write this t as t prime divided by omega naught. So t has units of seconds. 1 by omega naught has units of seconds. So what is the units of t prime? So what is the unit of t prime? Is it seconds?
Non-dimensional. No unit.
Yeah. T prime has no units. It is non-dimensional. Okay. So T prime should not be cell. T prime is for T prime equal to 3 seconds. Not possible. Or 0.3 second or 3 microsecond. No. T prime is non-dimensional. So I'm going to use, instead of variable t, I'm going to use t prime in my equation. So there are two places t occurs, here and here. So I'm just going to replace it. So what will I do is the following: d squared x by d. Now replace t. It's occurring twice, huh? dt square means is twice. So t equal to t prime by omega naught. So 1 by omega naught will come here, 1 by omega naught here, square. This is a square, like that. So I don't want to write like 1 by omega naught square, I'll just push it up, omega naught square. Okay, is that fine? So t is now replaced by t prime, and I have omega naught square. So I'll have 1 omega naught square x plus f naught by m cos. Now I need to replace this t as well, this t. So omega f t prime by omega naught. This is excellent. No? This equation is better. I can now take this omega naught. The omega naught square is common in both left hand LHS terms. So I can take it to the right hand side, and that equation becomes this is the equation. So d square x by dt prime. There is a prime sitting here, which is not very clearly visible. So t prime square plus x. So omega naught square from the left has come here, and cos omega f by omega naught t prime. So remember, this one is non-dimensional number, omega f by omega naught. Okay, and cos, sine, exponential, Bessel function, all of them take a non-dimensional number. I cannot say cos of 1 second. Cos of 1, and that 1 is not second or meter or anything. It's a non-dimensional number. So t prime is non-dimensional, and omega f by omega naught is a non-dimensional number. So this is something which you would like to vary. So compared to the forcing frequency compared to omega naught, how large is the forcing frequency? So when omega is equal to omega naught, then I get resonance. If omega f is much bigger than omega naught, then system basically follows the forcing. So we have different properties, and in fact we need to study for omega f bigger than omega naught, omega f less than omega naught, omega f equal to omega naught. Okay, so great. So now how many parameters do I have for this equation? Two parameters. Okay. Now you can treat this as a single parameter. You should not say that this is a 3 parameter, and this is another single parameter. This ratio. So the system has 2 parameters. I should work with these ratios. It's a single it's 2 different parameters. So I reduced from 4 to 2, which is good, and my time is now basically order 1. So I can vary t prime from 0 to, let's say, in fact 0 to 5 will be very good. So one unit will be something like one oscillation time of the well, it's not basically one oscillation, it's coming from here, or 1 to 10. This is great. 1 to 10, it will cover several oscillations. Okay, and I don't need to do it in microsecond or terahertz and so on. So all that is gone. But can we still reduce this to from 2 parameters to 1 parameter? So what should I do to reduce it to 1 parameter? Any ways to do it? So I still have one more way to reduce it. I can use non-dimensional x. Okay. So I need to basically non-dimensionalize x. Okay. X still has dimension. What should I do? So what is the length scale of the system? Please tell me. So you can see from here, you can match left hand side. So this size, this is dimension of x length. This is dimension of length. This is also dimension of length, right? So from comparing these two, you can see that my length scale is this length scale. You can also check from dimensions. Force is force by mass is acceleration. So acceleration is L by T squared, and omega s squared is 1 by T squared. So this is dimension of length. Okay. So my length scale, this is length scale. So what I do is I just gonna write x equal to x prime times length scale. So x prime is non-dimensional. X prime has no dimension. Okay. Now I substitute this x equal to x prime times that. You can see that this will come from both the terms in LHS. No? So and as a result, this term will get cancelled from LHS left hand side as well. So the final equation is this. Okay. So because when I substitute, you can easily see d square x prime by dt prime square. So this will be f naught by m omega naught square. Next term is x prime times f naught by m omega naught square. And this is f naught by m omega naught square cos of whatever. So this will cancel. So we are left with this equation. Okay. It has only one parameter, which is omega f by omega naught. Now I solve this equation. You can do it analytically, it's straightforward, inhomogeneous differential equation. Or you can also work on solve this in a computer. In a computer, I solve differential equation, which I'm going to discuss later in the course. So then plot x prime. So y-axis will be x prime, x-axis will be t prime, and we plot. Okay, depends on omega f omega naught. So it could be some function. Okay, depends on something like that. Now, given this plot, I can also construct back x. Somebody asked me, what is x prime? I don't want, but I want x, right? And that's my real variable. So how do I get x? So I can use this transformation. I know x at given t prime, my x prime is let's say 3. Then I multiply by this number to get the real x. In experiment, we have x. So I just multiply by this the factor, and I get x. For time, so it's well, I want in seconds. So I multiply 3 prime by the divide by omega naught square, then I get the time in seconds. Okay, so you can go back and forth from non-dimensional to dimensional, and from dimensional to non-dimensional as well. Okay, so these are the transformations to go back and forth. So let's look at the next example, hydrogen atom. So that was classical. Now let's work at quantum system. So this equation for hydrogen atom, time independent. Okay, I am not putting time here. So time independent. We can also work with time dependent. Okay, but let's just work with time independent. So h bar is Planck constant, m is mass of the electron. It should be really the reduced mass, but let's just ignore that part. Is mass of the electron. E is electron charge. R is a distance of the electron from the nucleus center. And E is the energy of the system. Okay, so I need to non-dimensionalize it. And this is particularly important. So h bar is a small number, m is in SI unit, no? M is a small number, E is a small number. So we don't want to work with those small numbers. So what should I do? So we need to find length scale of the problem. Okay. So what is the length scale in this problem? We don't need to worry about time scale here. There's this nabla, which is 1 by is a derivative. So we need to get rid of it by length scale. So I need to find the length scale. One idea is to get it from your memory, but we don't need to get from the memory. I can look at these two terms. Well, yeah. So I and figure out the dimension of length. So let's see. So let's say R naught is the dimension of the system. I think I call it RA. This is RA. So h bar. So what is the dimension of the first term? H bar squared by 2me. 2, ignore 2. This is the number. And this nabla is derivative, second derivative, with length. So that is the dimension of the first term. Second term is e squared by r, ra psi. So psi cancels, 1 ra cancels. So ra equal to h bar squared by m e squared. So this is the length scale of the system. I'm working with CGS units, huh? Otherwise I'll have to work with 4 pi epsilon naught, but I'm working with CGS. So please keep in mind the CGS units. With SI you'll have 4 pi epsilon naught, but you can work with that as well, no problem. Epsilon naught is another parameter. You can also work with dimension analysis. So you know the dimensions of h bar, me, small e, and you can construct the length scale. Okay, I'm sure you've done in your earlier courses. Even in school, people are doing now dimension analysis. Now use this dimension to non-dimensionalize. So this is my RA, and this one energy. What is the dimension of energy? So E squared by RA. Okay? So this is if I put a minus sign, that's a potential energy. So this is dimension of energy. Or this scale, I should call it energy scale. So this is length scale, and this is energy scale. Now I will write R equal to R prime times RA, and is hidden there. E equal to E prime times EA. So what is the dimension of R prime now? R prime is dimensionless. And dimension of E prime? E prime is dimensionless because E has dimension of ergs, E has dimension of ergs, so the two dimensions cancel. So E prime is dimensionless. So E prime will vary from 0 to a finite number, which will be 3, 4, 5. Okay. So, but it won't be a very small number. Okay. So that's the advantage of working with E prime. Also R prime. R prime is order 1. So now we need to rewrite the equation. So we found out the two scales, length scale, energy scale. Now let's work out the, so this is what I've done. Now I substitute here, okay? Now, so this is what we need to do. So minus h bar squared by 2me. Now gradient is a Laplacian, okay? So it's second derivative. So it is division of what? 1 by length, no? So I'm going to write gradient equal to gradient prime. So by RA. Now this gradient prime has no dimension, this one. So it is basically d by dx prime, d by dy prime, and so on. Is that clear to everyone? If I want second derivative, then I need to do here, here, and here. I presume it's clear to everyone. Okay, because I want this Laplacian prime to be dimensionless. So I need to divide by RA squared. So for this term, 1 by RA squared will come. Laplacian prime square psi. I'm not non-dimensionalizing psi. Psi can also be non-dimensionalized, but it appears in all the three terms. So basically, it doesn't really matter for this particular problem. So E squared by R will be replaced by R prime times RA. Psi. E is replaced by E prime, E squared by RA. Psi. Okay. Now you see some nice things are going to happen. So E squared by RA is present in two terms, this term and this term. Now, so that will be getting cancelled. So now let's simplify the left hand side term. Minus bar squared by 2me. Now what is RA we found out? RA was, it is here, h bar squared by me e squared. So I need to make it square of that. So h bar RA squared. So h bar, no, so by the way, one RA I will keep it. I will not do both the RA. So one RA is going to come out from here. So only one RA you put. Please put one RA here. So I put out of RA squared, one RA I'm going to switch h bar squared by me e squared. So this h bar square will cancel, me will cancel, and you're left with e squared by RA for this term as well, right? This one, this e squared, and this RA. So all the parameters are gone, h bar squared, me, everything is gone. Now minus e squared by RA, r prime psi equal to e prime e squared by RA psi. So now we get rid of this e squared by RA, this one is gone, and this is gone. So it's a just simple algebra. We get this equation. Laplacian prime psi minus half minus 1 by r prime psi equal to e prime psi. Okay. Now, isn't it a great equation? I mean, what is the opinion of people? I don't need to work with h prime. I don't need to work with any e. This is what we should focus on. We should not focus on this parameters, the too many parameters. And mathematics, essentially, we solve this kind of equation. We don't solve this equation. Okay? Now, in computers too, we want to solve this equation because it is divide of any small number, large number. I mean, h bar squared, you put 10 power minus 68. That is bound to have more errors. That kind of things are gotten rid of in this framework. Okay, so this is what we will solve in computers. In fact, we'll come across this equation later in the course when we solve Schrodinger equation, and we are going to solve this equation. Now, we can also write in the wave function, and wave function is written in terms of r prime, not in terms of r. So wave function is this, is exponential minus r prime. Okay, now this is solved using mathematical analysis, Ligard polynomial and so on, but you'll find that this is the answer. I mean, okay, if you put h bar and so on, that's just makes it ugly. Okay, so these are nice looking wave functions, and you can just focus on the forms of the equation and forms of the solution, not worry about the parameters. There are many examples. Okay, I mean, one more example is quantum oscillator. So this is a quantum oscillator. So again, h bar comes mass omega x. So it has also quite a few parameters. H bar m omega. So we can non-dimensionalize using length scale, which comes from here. If you just work for this one, so square root h bar by m omega is the length scale. Okay, if you non-dimensionalize using that length scale, energy is E prime is h bar omega. Sorry, E prime. So this is the equation. If I now use these two scales of the system, I will get this equation. Okay. And we solve this equation in computer. And it has solutions, I mean, of course, exact solutions. What is the advantage of doing all this? So we can just summarize. I mean, you can. So this should be equations. So what are the advantages of this? Much less parameters. We saw that. I mean, instead of for oscillator, instead of 4, we had only one parameter. For hydrogen atom 2, energy E prime is the only parameter. Everything was gone. For hydrogen, for oscillator, one parameter, hydrogen atom, one parameter, oscillator, one parameter, and you focus on that, solve that. So less experimental simulations, we just need to vary one parameter to study the system. Parameters are order 1, like E prime and is order 1. Omega F by omega, not maybe not order 1. So this is, I would say, this statement is probably not quite true. Sometimes it could be large. Like for oscillator, I may be working with omega by omega not much greater than 1. Okay. So I kind of, okay, I should not say that this is order 1. But in general, order 1. Okay. Energy of the hydrogen atom, non-dimensional energy is order 1. Now, variables are order 1. So my x prime, r prime. So it will go from 0 to 5, but it don't go from 0 to 5 million. Okay? So that's advantage. Or 0 to 5 Armstrong. It's not that. And the equations are nice. So they are, computers like these equations. Also, I think as a human being, we should want simple equations to solve. Okay? So that's advantage. And is manageable and clear equation. So for even math analysis, these are good things.